So this is part 2 of the lecture video for experiments 8 and 9. And so in this video what I want to go through is prior syntheses of Prozac and then talk a little bit about the mechanistic details of the synthesis that we're going to be doing here. It is important to note that originally Prozac was, oops. So originally, Prozac was identified as a single enantiomer drug, that only one enantiomer of this molecule was shown to be effective, and consequently that enantiomer, it was important in early syntheses of Prozac to only generate that enantiomer. So if we go back and think about the topic of enantioselectivity and we think about prior syntheses, we have to think about a route, or we have to think about an approach that we can obtain a chiral molecule here. Okay. So when thinking about an effective route for uh, anything that's going to be made in a commercial setting, you need to think about the number of linear steps, your yield for each step, reaction conditions, and probably the aspect that you're least familiar with is ease of purification. And that, as it turns out, is probably the number one bottleneck in terms of identifying and synthesizing molecules that can be utilized as drugs. Okay, so this is Prozac. Um, if you have heard the stories of thalidomide, thalidomide is a very old drug that was used in the 1950s as an antiemetic. So antiemetic means that it is prescribed to deal with nausea for pregnant mothers. And what was found is that um, people that were taking thalidomide were highly predisposed to birth defects. And thalidomide was a very important molecule for a variety of reasons. It still is an important molecule to this day in our modern pharmacopoeia. Um, and the work that went into understanding how thalidomide caused birth defects allowed us to understand the fact that it was only one enantiomer of thalidomide, so one enantiomer of this chiral center, that caused the birth defects, and then the other enantiomer was the effective drug. And so because of thalidomide, every drug that has any chiral centers in it coming forward through the FDA must be enantiomerically pure. Um, that that is until the drug company can prove that both enantiomers are safe. But regardless of those studies, that any drug coming forward today has, if it has a chiral center, which we do have in this case, any drug coming forward must be enantiomerically pure. Okay. So because of that, there had to be approaches that would enable the synthesis of an enantiomerically pure product. And so the first step was from a laboratory where the PI's name was Barry Sharpless. And this became famous because there was one specific step, which was the epoxidation of this double bond in the context of this synthesis, where you would get an enantiomerically pure epoxide out of this. And this chemistry is now referred to as the sharpless epoxidation. Then you can use a hydride reagent, so imagine a hydride reagent coming in, reacting there to give you this enantiomerically pure alcohol, and then you make a mesylate out of this, which is basically making this into a leaving group. You then react that with a nitrogen. So here's your lone pair. It will react here and kick off your mesylate to give you this molecule, and then all you're going to need to do at that point is add in your trifluoromethyl aromatic group, which is that reaction is experiment 3, which we will not be doing. A second approach is to start with a ketone and then do a chiral reduction. So these are a variety of reagents that are not dissimilar to sodium borohydride, but they react in such a way, because they have these chiral pendant groups on here, that you can generate a chiral alcohol from an achiral ketone. These are a series of reagents that were developed by the Nobel laureate E.J. Corey, and these reagents are referred to as selectride reagents. So imagine they're just a hydride reagent, but the way that they react with a ketone gives you selectivity in your alcohol product. So once you get to this step, it's not dissimilar from the sharpless synthesis. You're going to add in your methylamine at this point, and then do your aromatic substitution reaction. The synthesis that we are going to be doing is a little bit different. We are going to start out with something that is referred to as a Monish reaction. So what we are going to do is we are going to take this molecule, react it we are going to take this molecule, react it with dimethylamine to form a transient imine. This is going to go through an equilibrium to give us this enol intermediate, and that is going to react with this intermediate to give us something that looks like this. So then we will reduce this with sodium borohydride, and then this is where we will end. That will be our final reaction. We'll do the Monish reaction, then we'll do the sodium borohydride reduction. We will not do the aromatic substitution reaction. And this goes through mechanistically how you form the Monish reagent, and then how that reaction happens. Okay. This then goes through mechanistically how the borohydride reduction goes, and we are not going to do it, but this, in a very chemically incorrect way, goes through how the aromatic substitution reaction happens. There's a little bit of information here on mechanistically how Prozac works, but I'm not going to really go through that. And that pretty much takes us to the end of this lecture.